delay, we are starting our next book, which is by Carlos de Prisco from the Universidad de Los Andes in Colombia. And he's going to talk about local Ramsey property in abstract spaces.
Thank you very much. I'd like to start by thanking the organizers for this very nice meeting and for giving me the opportunity to talk about some ongoing work about Ramsey sets in a very general sense. So I'd like to start by making a short review of Ramsey property for sets of reals. So we look at the collection of all infinite subsets of natural number of the set of natural numbers, and we can give this set topological structure actually in several ways. One way is to look at the basic sets defined by fixing a finite set of natural numbers and an infinite set of natural numbers, and then looking at all the infinite subsets of n which have the finite set as an initial segment and which are contained in the infinite set we chose to fix. This could be empty in some cases, but in any case they generate a topology on the space which is called the Ellentuck topology. Nowadays it's actually the exponential topology. We will also consider the metric topology, which is a topology inherited by the set of infinite subsets from the collection of all sets of natural numbers. Look at characteristic functions and given the product topology with n with the discrete topology. Well, we can see that a subset of the space of infinite subsets of omega has the bare property with this with respect to this Ellentuck topology if for every basic set we can find a smaller basic set which is contained in our subset or is disjoint from it. If we strengthen this a little bit, we get the Ramsey property. Subset of our space is Ramsey. Actually, this is was originally called completely Ramsey. If for every basic set there is another one which is obtained only by shrinking the infinite part of the basic set, which is contained in our collection or is disjoint from it. So obviously the Ramsey property implies the bare property, and the relation between those two things is probably the central topic of the talk. Galvin and Pricri in the 60s proved that all there are some misprints, as you have noticed. Proved that all Borel subsets in the metric topology of the space are Ramsey. This can be extended to the Ellentuck topology. Silver showed that analytic subsets have this Ramsey property, and Ellentuck gave a topological proof of this result by showing that a set has the Ramsey property or is Ramsey if and only if it has the bare property with respect to the Ellentuck topology. So going back, we have that Ellentuck showed that in this space these two properties are equivalent. Okay. Now, Adrian Matthias, in his dissertation, explored the consistency of having all subsets of the space with a Ramsey property. The published version of this appeared, is that correct, in Happy Families, in the paper Happy Families. And in this paper he shows that this property, all subsets of the space are Ramsey, holds in Solovey's model obtained by collapsing an inaccessible cardinal and then looking at the definable sets within that model, within that extension. As far as I know, it remains open whether this consistency is can be obtained without assuming existence of inaccessible cardinals. In Solovey's model, all sets of reals are Lebesgue measurable, and we know now that we need the inaccessible hypothesis to show that, as well as to show that all sets in that model, well, to get a model where all sets have the perfect set property, but for the consistency of all sets have the bare property, inaccessible are not needed as a hypothesis. For the Ramsey property, this is not known. Now, Matthias also introduced a notion that he called happy families in his paper, and to define that, I will actually use a different term. A subset of the power set of n is called a coideal if it is a collection that is, well, does not contain finite sets. Actually, it doesn't contain singletons. It's closed upwards. If A is in the collection and B contains A, then B is also in the collection. And it has also this third property, which says that if you have a set in your collection, in the coideal, and you split it into two parts, then one of the parts must be in the coideal. So in particular, coideal is a proper subset of the power set of the natural numbers invariant under finite changes. So what Matthias called the happy family is a coideal H and the natural numbers, which is selective. And selective means that it admits diagonalizations in a very precise sense. If we have a decreasing sequence, a coideal then is called selective if for every decreasing sequence of elements of H, decreasing in the sense of containment, then there is an element of the collection, a set in the collection, such that if you look at the tail of B above a number n, then this is contained in the nth element of the sequence. The selective coideals were called happy families by Matthias, and they can be characterized by these two as collections of subsets of n having the following two properties. First one is that they have the collection admits diagonalizations for decreasing sequences in a more general way. If we have a decreasing sequence of elements of the collection, then there is one which is almost contained in every of these sets of the collection. And then the second property, which is that if an element of the coideal is partitioned into finite sets, then there is an element of the coideal which is a subset of the original element n, such that for all k, the intersection of this new set with the kth finite set is has at most one element. So it's a partial selector. So examples of selective coideals were given in the paper that I'm referring to, Happy Families. The collection of all infinite subsets of n is a selective coideal. Another example is that if you have an infinite almost disjoint family of subsets of n, then the collection of subsets of n that cannot be covered by a finite number of the elements of the family is a selective coideal. So we continue reviewing some of the results in Matthias's paper. The notion of Baire and the notion of Ramsey were extended or localized to a happy family or a selective coideal in the following way. We say that a subset of our space is H Baire if for every basic set with infinite part in the collection H, then there is a smaller basic set also in the same family. I'm saying that the top part of the smaller set is also in the coideal that is contained or is disjoint from our subset of the space. If the second alternative always occurred, then we say that the set A is meager, is H meager. And similarly for the Ramsey property, a subset of our space is H Ramsey if for every basic set with A in the collection H there is a smaller set that preserves the root, preserves the finite part, only shrinks the top part, which is in the collection, and such that this smaller basic set is containing A or is disjoint from A. If the second alternative always occurs for A, then A is said to be Ramsey null, a Ramsey null set. Well, in this well-cited paper, Matthias showed that if H is a selective coideal, then every analytic subset of the space is H Ramsey. He also showed that for a selective coideal H, then every set for every set subset of our space, the set is H Ramsey if and only if is H Baire, which is an extension of Ellentuck's original result, and also that in Solovey's model obtained by Levy collapsing, now a Malo cardinal, for every selective coideal. Well, actually, this should be expressed in a more precise way. If we Levy collapse a Malo cardinal and we take any selective coideal in the extension, then every definable subset of our space, for example, every set in L of R of that extension is H Ramsey. In this case, it's known that by result of Iceworth, I think, that this hypothesis is needed. You cannot avoid the hypothesis of a Malo cardinal, and you cannot even reduce it to, say, inaccessible cardinal. Very well. To get his results, Matthias considered two forcing notions beside the ones that I've mentioned already. Forcing with the coideal and almost containment, this forcing notion adds a selective ultrafilter containing H. And also, Matthias considers Matthias forcing, which is relativized to the coideal, meaning we force with the conditions that are the basic sets in which the infinite part belongs to the coideal. This forcing notion adds a real, and the properties of these generic reals are described in this paper. And my objective for this talk will be to explore extensions of these results in different ways. Well, I want to mention that Ilias Farah, in a paper called Semi-Selective Coideals in 1997, introduced a weaker notion of a coideal that is called semi-selectivity. So a coideal H on N, or collection of infinite subsets of N, is semi-selective. Now we have a different kind of diagonalization property. If for every sequence of dense open subsets of the ideal and every A, we can find a B containing A, which is also in the coideal, such that this B diagonalizes the sequence of dense sets in the following sense. For every N, the top part of B above N belongs to the dense set. Or another way to say it is that we can pick an element of each of the dense sets, which is a decreasing sequence, and the set, and below every A there is a B that diagonalizes that sequence. The collection of diagonalizations is dense in H. So if you remember, Ellentock's result was that every Baire set is Ramsey, and vice versa. Every set has the Ramsey property if and only if it has the Baire property with respect to the exponential topology. Now, before that, I would like to see how semi-selectivity is actually can be also characterized by these two properties that we use for selectivity, but we relax the first of the two properties. The second property is actually the same. An element of H which is partitioned into finite sets admits an almost selector in the collection H, and the top part with these dense sets instead of the decreasing sequence, we actually are requiring something that is weaker, in the sense that for selectivity the property we had is sigma closeness. Here we only have distributivity of the collection H. So Farah showed that if the coideal H is semi-selective, then, as before, said is Ramsey if and only is H Ramsey if and only if it is H Baire, but the semi-selectivity property is actually equivalent to this equivalence between these two properties. Farah so extended Matthias's results to semi-selective coideals. He studied the two forcing notions now relative to a semi-selective coideal, and he showed that the semi-selectivity property for the coideal is actually equivalent to some properties of Matthias forcing relativized to the coideal. H is semi-selective if and only if this forcing has what we'll call the Matthias property. This means that any generic real, a real is generic if only if all of its subsets are also, all of its infinite subsets are also generic, and that's also equivalent to the Prisco property, by which I mean that given a condition and given a sentence in the forcing language, then we can decide that sentence by taking a stronger condition that only shrinks the top part or the infinite part of the condition. Okay. Now, can be shown that in a solvable model obtained by collapsing a Malo cardinal, the same as Matthias's result, then every definable set, I didn't write the precise statement, any definable set in the extension obtained by Levy collapsing the Malo cardinal, and for every semi-selective coideal in that extension, the set is H. Ramsey.
I think when you wrote it, you meant solvable model to include the notion of definability. It's the definable.
That's true. I'm mixing up things. Here I'm saying that if I get the collapsing extension, then the definable set is there. But in the solvable obtained by that is the definable set. You're right. Thank you. Okay. So I would like to mention now a general framework for developing these ideas that was originally introduced by Carlson and Simpson, and later developed or modified by Todorcevich, which we will call topological Ramsey spaces. So we have a set R, a quasi-order defined on R, and a function small case r, which we will refer to as approximating function for elements of R. This is very abstract because I'm not saying what R is, I'm not saying what the approximations of elements of R are, but the idea is that if we have an element of R, then this function says that for every n we have the nth approximation of the set A. I will give some examples shortly, but the idea is that in this very abstract framework we can define basic sets in a similar way as before, saying that if we have an approximation and an element of the set R, then the basic set is the collection of all of elements of R which are below B and which have A as an approximation. So the basic example is the element space that I mentioned before, where R is the set of infinite subsets of the natural numbers, of the set of the natural numbers. The order relation is containment, and the approximations are initial segments. So the nth approximation of an infinite set is its first n elements. There are other more involved examples that I will mention. For example, the collection of finite subsets of omega with the relation of should I say amalgamation, probably. So we have now, instead of R is a set of block sequences of finite sets. We have a finite set, we have a non-overlapping finite set, and so forth. We have these are finite subsets of n, and then we say that if this is A, B is below A if we obtain B by picking some of these elements and putting them together and so forth, and getting another block sequence. And in this case, the function R, approximations are initial segments in the sense of the first n blocks. This is the nth approximation of the element of the infinite collections of finite sets, block sequences. But we also should keep in mind another space, which is the dual space of infinite partitions of omega. In this case, we will look at a partition of omega into infinite sets, and we can order these parts by looking at the first element of each of them. We order them like this, etc. We have all these partitions. The order relation in this case is also a sort of amalgamation. We can merge some of these parts together, and we obtain a partition which is below the original one. And the approximations are partitions of finite sets. We look, for example, at this first element of the fourth piece of the partition, and then we look at this part, and this is the fourth approximation. In all of these cases, the original object in R, is the union of all its approximations. In the sense, it's a limit of all approximations. And we will say that the space R is closed if it is a closed subset of the sequences of approximations that are coherent. Well, many other examples have been investigated. Natasha, Dobrinin, Mijares, of course, Todorcevich in his book on Ramsey spaces, Trujillo, who was a student of Natasha Dobrinin, have found and studied other very interesting and more involved examples of Ramsey spaces. But we can try to develop the same structure as we did in the Ehrenberg space for Ramsey spaces. So a subset X of a Ramsey space has the property of Baire. Well, if we look at the analogous of the Ehrenberg topology in this space, and the set has the Baire property with respect to that property. So this is now our basic definition. A subset of X of a Ramsey space has the Ramsey property if for every basic set which is non-empty, recall that basic spaces, these basic sets are defined this way, as the collection of all things that are below B that start with A as some finite approximation. So a set has the Ramsey property if for every basic set I can shrink the top part, shrink in the sense now of the order relation in the space, or the pre-order relation in the space, to obtain a smaller set which is contained in X or is disjoint from X. A set is Ramsey null if we get the second alternative for every basic set. Okay, so we say that such a space is a topological Ramsey space if we have the equivalence between the Baire property and the Ramsey property for that space, and the equivalence between being meager and Ramsey null. So the three examples I gave, the Ehrenberg space is a topological Ramsey space. Also the set of finite sets with this order relation, and the set of partitions of omega. The three examples satisfy this definition. Ehrenberg proved, well, this is the original result of Ehrenberg, and the theory that Todorcevich developed is that when is a space like this a topological Ramsey space? When do we have these equivalences? And he gave some axioms that guarantee that a space like that is a topological Ramsey space. And I will try to describe these axioms very quickly. They look like very technical, but I think they are very natural. These are axioms 1 to 4. The first axiom is what we can call metrization, is that the serious approximation for every element of A is the empty set. If we have two different elements of the space, then at some finite stage they differ. They already differ. We can detect their difference in some nth approximation. If the nth approximation of A equals the mth approximation of B, then n has to be equal to m, and all the previous approximations must coincide. The second axiom that we can call finitization is that there is a quasi-ordered sub-fin on the approximations, on the collection of approximations, which behaves like that. If A is less than B in the quasi-order of R, that happens if and only if for every nth given an approximation of A, this is obtained by the order sub-fin from some approximation of B. The second property is that given an approximation, the collection of smaller approximations is finite. And the third part, or the third condition in this action says that if A is less than B, these are two finite approximations, one is below the other, then we can find I'm sorry, if we take an initial segment of A, then we can find an initial segment of B which is below it. I'm not reading correctly. If A is less than B and we take a finite initial segment of A, then we can find an initial segment of B which are in this relation. As I mentioned a few minutes ago, we say that R is closed or metrically closed if it is a closed subspace of the sequences of approximations with the product topology obtaining by giving the set of approximations the discrete topology. Well, there are two more axioms that I would like to consider, but first I think it's convenient to give some notation and definitions. So we say that given an element of R, the set of approximations relativized to A is the set of approximations that are somehow obtained by taking elements of A. This means, in the case of finite sets, that, for example, if we take a block sequence of finite sets, we can take several of them, and that is an approximation of some other set, but it's below some approximation of A. So if I take 3 of those finite sets from any part of A, what I get is an approximation that is below some initial segment of the collection. And for example, if I take say this, and that's what I call A. These two sets are below, say, the 1, 2, 3, 4, the 5th approximation of A, but it's also below the 4th approximation of A, and the smaller n I can get is called the depth of this small a in big A. And that's what is the next definition. And finally, when I say the basic set NA, I will use this to refer to the basic set obtained by looking at the nth approximation of n of A, and then the rest, and then the whole set A. With that notation, the other two axioms are the amalgamation axiom, which is also very natural. If we have a basic set like that and a set B, which is, this means that B starts just like A up to the nth approximation of A, and then continues below A. If we have a B like that, then this set is also non-empty. Well, if this set contains an element, this set is also non-empty. If this basic set contains an element B, then we can find something in this neighborhood, a set in R, or an element of R, which starts just like A up to the nth approximation, and such that this basic set is contained in the set with the same final approximation as first coordinate, and the set or the element B of R as second coordinate. The last axiom is called the pigeonhole principle, and if you look at an approximation small a and an element of Ra with depth n, and then you look at the collection of all larger approximations, but just one step more, one unit larger, and divide that collection into two parts, O and its complement, then we can find a B in this basic set, such that all approximations of this slightly larger length, which are obtained by looking at elements of this neighborhood, are contained in O, or all of them are contained in the complement of O. If you rephrase this principle for the Erlentok space, all you're getting is Hausdorff's pigeonhole principle that was referred to in the first talk of the conference. You have an infinite set and you partition its elements into two parts, then one of them has to be infinite. Well, with those axioms, Todorcevic proved that you can reproduce the theory of Ramsey properties. These axioms are actually designed, this is my view, to be able to reproduce Galvin's argument that shows that basic open sets in the metric topology are Ramsey. This argument uses something that has been called the combinatorial forcing, accepting or rejecting, and you can reproduce that using these properties expressed in these axioms. So I'd like to, the last part of my talk refers to work in progress with Jose Mijares and Jesus Nieto, both well, actually, Mijares is now in Denver University. Nieto is in Caracas, Venezuela. We propose a notion of coideal for Ramsey spaces. So in a set like that, R with the order relation or the quasi-order relation and the approximations satisfying these axioms, a collection of elements of R is a coideal if it is closed upwards and satisfies the relativized versions to H of the last two axioms. So I won't go into reading the details, but we have the amalgamation property mod H and the pigeonhole property mod H. That's what we call a coideal. Just want to mention that this pigeonhole property relativized to H actually gives something which corresponds to the property of coideals that says that if you have an element of a coideal and split it into two parts, one of the two parts must be in the coideal. So that's contained here somehow. So from the theory of abstract Ramsey properties that Todorcevich developed in his book called Introduction to Ramsey Spaces, if this collection H is closed in the topology of infinite sequences of approximations, then this has this becomes a Ramsey space in the localized version, where we look at basic sets in which the second coordinate is actually an element of H. Now, if H is not closed, what we want to do is to explore what do we need from H so that we can still have this Ramsey property, or the equivalence between the Baire property localized to H and the Ramsey property localized to H. And it turns out that the notion of semi-selectivity is enough to get that. This also will allow us to study the corresponding forcing notions. Now we have the coideal subset of R with almost reduction, which corresponds to almost containment, and the analogous of the Matthias forcing notion F sub H. And this will satisfy, these forcing conditions will satisfy abstract versions of some of the properties I mentioned earlier for the case of the Ellentock space. So we give a definition of diagonalization for a family of elements of the set A, indexed by a set of approximations coming from an element of the space. And we say that another element of R is a diagonalization if for every approximation in B, every approximation extracted from B, we have this containment. A comma B is contained in the 8th element of the collection with this root A. And we say that coideal is selective if for every A and every family of this sort, there is a diagonalization of that family in the family H. A subset of the space is dense open if it is dense open in the sense of this pre-order relation. This is nothing new. And the notion of semi-selectivity is now defined in terms of diagonalizations of families of dense sets, dense subsets of the coideal H. So the definition is similar to the previous one, and we say that a coideal H contained in R is semi-selective if given any family of dense sets indexed by approximations coming from an element A of H, such that this each element of this family is dense open in H, relativized to the set A, then below every B in H relativized to A, there exists a C in H, which is a diagonalization. So the set of diagonalizations is dense in some sense, and we can prove with this generalization something analogous to Galvin's lemma, given a semi-selective coideal of a space like that and a collection of finite approximations and set A in H, then we can and a finite approximation A, we can find a B such that if we relativize everything to B, our collection of finite approximations is empty, or every element of this basic set starts with a finite approximation coming from F. With this technical lemma, then we can prove that the basic metric open subsets of R, which are defined, well, as you would imagine, they're defined, are H Ramsey. The open subsets in the metric topology of R are H Ramsey. And also, it can be shown that if H is a semi-selective coideal here, then a set is H Ramsey if and only if it is H there. We believe that there is also the reciprocal of this. If we have this property, then the selective for a coideal H, then the coideal must be semi-selective. But proof hasn't been written, and I think this requires only that these sets are both closed in the collection of sequences of finite approximations. So I'm not claiming it now, but I think it can be proved. So we also can define a notion of ultrafilter contained in R, which is essentially a collection which is closed upwards. I missed that, I guess. I should say that this collection is closed upwards with respect to this relation. Then if we have two elements in the collection, then this is it. I'm sorry. I guess I'm trying to hurry up and I'm not reading. So this is closed upwards. What I missed then is that, this is the finite intersection property expressed in terms of our setting, and maximality property. And then we also add the relativized versions of these two axioms to make it a coideal. So an ultrafilter, in this sense, is always a coideal. And with this almost reduction property, which corresponds to almost containment in the sense of our order relation, then we can show that if we use this H is a selective coideal, and we use this relation, we get a forcing notion which is sigma distributed, so it doesn't add any new elements of R, but adds a selective ultrafilter to the ground model. And I guess finally, if we look at the corresponding notion of Matthias forcing in this context, we force with these basic sets, with these conditions, within, well, what would be the natural way of defining the ordering, then this forcing shares many properties with the original Matthias forcing relativized to a happy family. And for example, we have that if U is a selective ultrafilter in a transitive model of CF and DC or DC of R, then forcing over this model with M sub U adds a generic real with the property that it's almost contained in any element of the ultrafilter, of the original ultrafilter. Actually, any element of R is NU generic if and only if it's almost contained in every, not contained, it's almost a reduction of every element of the ultrafilter. And well, this forcing, when H is a semi-selective coideal, has these two nice properties that I mentioned before, the analogous of the Prickry forcing, which is decision by just shrinking, decision of a formula by just shrinking the top part, and the genericity is preserved by infinite reductions. This is what I call the Matthias property. And so we can get the consistency of all subsets of R have the Ramsey property in an extension collapsing. Well, in this case, I don't know if a Malo cardinal would suffice. It probably would, but I can only do it with a weakly compact cardinal because the semi-selectivity property is like a higher order property that I cannot reflect down just with malo to a V kappa, which is kappa inaccessible. So it seemed to need a stronger property. So just to finish, I want to mention that if we look at the space of partitions, like partitions of omega, the dual Ramsey space, then these results give that under suitable large cardinal hypothesis, we can have the consistency of all subsets of the dual space of infinite partitions of omega are Ramsey in this more general context. And I will finish with that.
So, thank you very much, Carlos, for this very nice talk, especially appropriate since Matthias is celebrating his 70th birthday, and we're celebrating it with him, so remembering all this work. Are there any questions for Carlos? Yes.
I don't want to saturate the meeting with my reminiscences, but could I draw attention to the fact that my dissertation of 1968 has now been scanned and it's on my website in Cambridge, so anyone who's interested can ask for a link.
Well, by the way, the notion of capturing a dense set that is in your dissertation is crucial to prove this version of Galvin's lemma, and the fact that the forcing M sub H has these nice properties.
Okay, have questions? Yes?
So, do you have some result about which would say that the selective outer filters you define for Ramsey spaces correspond exactly to generic outer filters for forcing with some?
I think that's that's what I suspect, and I think we can prove that. But this is still in progress, and there are some things that have to be checked. But I think this we get that result, and then there are many these other spaces that satisfy these axioms that I didn't mention. For example, things coming from variable words and sequences of finite variable words that would also be treated in a similar way, and we do get some consistency results about those combinatorial spaces from this general framework.
Maybe a naive question that everybody knows the answer to, but is there a local version of is there a local Ramsey theory of forcing which is
you mean with a measurable?
We have these various versions of Matthias forcing, but not strictly forcing, so there must be some other local.
Probably, but I haven't really looked into that.
Other questions? Well, in this case, let us again thank Carlos for this very nice.